So notice that in the previous slide we had work is equal to charge times delta V. We had defined potential over Q is delta V, and instead of potential we wrote work done. So work done is always measured in joules and Q is in coulomb. So delta V is in joules per coulomb. So you defined 1 joule per coulomb as 1 volt. So basically 1 joule of work must be done to move a 1 coulomb of charge through a potential difference of 1 volt. So 1 volt is equal to 1 joule per coulomb, or you can say 1 joule of work must be done to move 1 coulomb of charge through a potential difference of 1 volt. Let us now talk about electron volt. So electron volt is work done to move an electron or proton. So both electron and proton carry a charge E through a potential difference of 1 volt. So this basic unit E, the basic charge E is 1.6 into 10 to the power of minus 19 coulomb. So 1 electron volt becomes 1.6 into 10 to the power of minus 19 joules. So let us do an example. So you have two parallel plates at a distance d from each other and they are connected to a battery. So the battery is of 10 volts. So therefore you write delta V as 10 volts. Now distance between the two plates is say 0.5 times 10 to the power of minus 2 meters. So delta V is given as E times D. So this we saw in the previous slide. Now the angle between the distance and the field is 0 degrees. So you get ED cos 0. So that will give you E times D. So you rearrange the formula, you get E is equal to delta V by D. Now plug in the value of delta V and D. You get the value of electric field as 2 into 10 to the power of 3 volts per meter. Now we talk about electric potential due to a point charge. So we have seen in the previous slide that the change in potential, that is final potential, which we will write as V subscript F minus initial potential V subscript I. This is given as minus initial distance, which is Ri, and final distance say is Rf. Then you have dot product of electric field and the small displacement. Now electric field due to a charge Q, this we have seen in previous chapter, is given as kq over r square. So this is electric field at a distance r from a charge q, and since distance is measured in r square or r, the small displacement is dr. So now we just integrate it. Minus kq is constant, it comes out. So limits of integration are initial distance ri to final distance rf, 1 by r square dr. So integral of 1 by r square dr is minus 1 by r, and you have initial distance ri to final distance rf. So we get the change in potential, that is V final minus V initial. This you can see is minus kq times, you will have 1 by ri minus 1 over rf, or you could have directly written this, taking the negative sign out. You could have just written this as kq over 1 by rf minus 1 by ri. So this is a formula for change in potential between 2 points. You have initial potential and final potential. Now we want to talk about zero electric potential. Now zero electric potential is associated with the distance r equals to infinity. So we want to put 1 by infinity as 0, and thus if initial distance is infinity, then initial potential would be 0, because if initial distance is infinity, we want to put potential there 0 because electric field is also 0 there. So in equation 1 you put Ri as infinity and you put Vi as 0, and you put Vf equals to V. We also put the distance as R. So if you put Rf as R, you get V equals to Kq over R. So we have just plugged in Vf as V, Rf as R, and Vi as 0 and Ri as infinity. So this formula which we get, V equals to Kq over R, is electric potential at a distance R from the charge Q. So this formula V equals to Kq by R can also be interpreted as the amount of work done in bringing the charge from infinity to present position, because this is same as saying as putting Vi as 0, and Vi is associated with distance Ri and Ri is infinity.